Let's continue talking about erythrocytes, and in particular hemoglobin, because that's the magic molecule. So remember, red blood cells are bags of hemoglobin. Their only real job is to carry oxygen. Now, hemoglobin binds reversibly with oxygen. What does that mean? It means that it can grab oxygen and it can let it go. So the structure of hemoglobin, it's a protein globin, all right? Globin chains are protein. It has 2 alpha and 2 beta chains. That's not really terribly significant. Just shows that it has a kind of a symmetrical shape. There's a heme pigment bonded to each globin chain. And in the middle of each heme is an iron atom. And it can bind 1 molecule of oxygen. That's O2. So that's 2 atoms, 1 molecule of oxygen. So notice, therefore, that the hemoglobin has 4 globin chains. So, therefore, how many molecules of oxygen can it carry? 4, 1 in each globin chain. Every hemoglobin protein can carry 4 molecules of oxygen. All right? And there you see, in the upper right, you see in the middle of that heme chain is that iron atom. There it is, and it grabs hold of that. See the O double bonded to the O? That's what's going on there. That's what it's holding. Oxygen loads in the lungs and produces what we call oxyhemoglobin. So hemoglobin that has oxygen attached to it is a bright ruby red. Then, when we get to the tissues, oxygen unloads. Hemoglobin lets go so that your cells can get the oxygen. That produces deoxyhemoglobin. That's dark red. In general, arteries carry oxygenated blood, and veins carry deoxygenated blood. That's why arteries are more red, veins are more bluish. And they're not really blue, it's just the way it looks when you look through the skin. There are a couple exceptions to that. The 2 exceptions are the pulmonary arteries and veins and the fetal umbilical arteries and veins. They're backwards. In that case, it's the veins that carry oxygenated and the arteries that carry deoxy. But those are the only exceptions. Now then, in the tissues, it picks up carbon dioxide. That produces something called carbaminohemoglobin. Now, as it turns out, hemoglobin only carries about 20% of the CO2 in your blood. Do you know how the rest of it is carried? We actually know this. We've seen it before. We know the reaction. Yeah, bicarbonate. Remember how carbon dioxide combines with water to form carbonic acid, which then can dissociate into a hydrogen atom and a bicarbonate ion? Well, in the lungs, remember that a reaction can proceed in the opposite direction, and so the CO2 will come apart and it will be exhaled. And in the bottom right, you see the oxygen hemoglobin dissociation curve. Really, what this says is that in the tissues, due to the pH, hemoglobin is more likely to let go of the oxygen, whereas, and that also due to the partial pressure of oxygen, in the lungs, it's more likely to grab a hold of oxygen. We might talk more about that later. So oxygen binds to what portion of the hemoglobin? Yeah, it's the iron atom. That's what actually grabs it. Okay, hematopoiesis. Hematopoiesis can also be called hemopoiesis. The root word there, Greek word, poiesis, means to create. So hematopoiesis means to create blood cells. So it occurs in the red bone marrow of the axial skeleton and in the proximal epiphyses of the humerus and the femur. All right, so that's where you have red bone marrow. That's where you're making blood. Hemocytoblasts, also called hematopoietic stem cells, they give rise to all formed elements. So these stem cells make red blood cells and white blood cells and platelets. All 3 are made by the hematocytoblasts, the hemocytoblasts. Hormones and growth factors will push this stem cell in one direction or another. In other words, how does it know whether to turn into a red blood cell or a white blood cell or a platelet? Well, hormones and various other growth factors will influence it as to what it should turn into. New blood cells enter the blood through sinusoids. We'll see there are different kinds of capillaries, and there are sinusoidal capillaries that have huge openings, and that's how blood cells get into blood. So continue with hematopoiesis. So erythropoiesis means specifically making red blood cells. Hematopoiesis means making all formed elements. Erythrocyte means making red blood cells. Regulated by the hormone erythropoietin, and that's a very famous hormone because that's the kind of substance that Lance Armstrong used to cheat. A lot of people say, oh, he used steroids. No, he didn't use steroids. Steroids would be really stupid. That wouldn't help. You don't need tremendous physical strength. What you need is endurance. So EPO, a lot of performance athletes have cheated over history using this. Marathon runners were the first ones, and cyclists are the ones who then became famous for it. So what it does is it causes you to make more red blood cells. Right? If you make more red blood cells, then you can carry more oxygen, can't you? And that leads to higher endurance. So that's why endurance athletes cheat by using erythropoietin or some similar compound. This is made primarily by the kidney. Now, leukopoiesis means the formation of white blood cells. In this case, there's no hormone. There's no leukopoietin. Regulation varies in response to pathogens. So in other words, when your body gets invaded by bad guys, by pathogens, bacteria and viruses and so on, it causes white blood cells to release little proteins called cytokines. Those include things like interleukins and colony-stimulating factors. And those, in turn, then influence the formation of the creation of white blood cells by the hemocytoblasts. Instead of making red blood cells, they'll make white blood cells. Colony-stimulating factors are the big ones there. Thrombopoiesis means making platelets. Again, remember, we don't actually have thrombocytes, but thrombopoiesis is still the name used for creating platelets. And there is a hormone, thrombopoietin. Just like there was erythropoietin, there's thrombopoietin. That influences the hemocytoblast to turn into platelets. It stimulates megakaryocyte production. So a megakaryocyte is a big, giant, massive cell that essentially explodes. And when it explodes, it leaves little chunks behind, and each one of those little chunks is a platelet. Okay? Now, what happens to erythrocytes? They only live 3 to 4 months. Remember, I said that in general, formed elements don't live long. Memory cells, white blood cells, T and B memory cells are exceptions. They may last your whole lifetime. But most blood cells don't live very long. And it's because they're out getting beat up all the time. Remember, in particular, the erythrocytes are squeezing through capillaries, and that's really hard on them. They're scraping against the sides of the wall of the capillary, and so they get beat up and they have to be recycled. Once old red blood cells become fragile and the hemoglobin begins to degenerate, macrophages will engulf dying red blood cells in the spleen or liver. So those are the two organs where you recycle your old blood cells. It's mostly the spleen. That's the primary organ, but if you have problems with your spleen, then the liver can take over. The heme and the globe are separated. Now iron is a very reactive atom, and it can cause big trouble if it travels unaccompanied throughout your body. So remember, we had transferrin, which is one of those plasma proteins, that helps transport iron through the blood so that it doesn't damage the cells and tissues of your body. So the heme has to be very carefully handled, so it's transported by, like, transferrin. The globin, since it's just a protein chain, you just break it apart, turn it back into amino acids, and those are incredibly useful. Your body can use them for all kinds of things, make more proteins out of them. So that part's easy to recycle. It's the heme group, because of the iron, that needs special attention, special care. So heme is converted to biliverdin, which is converted to bilirubin. Verde, green. And rub, the root word means red, but it's more of a yellowish. So what happens here is that the red of the erythrocyte turns into a green pigment and then ultimately turns into a yellow pigment. So that's what happens. You know how sometimes you get a bruise like a pretty good solid bruise. Somebody hits you really hard, or you get hit by, a baseball or something. And the bruise, you can see all kinds of colors in it. There'll be red and purple and green and yellow. Yeah, that comes from the breakdown of the heme, of the pigment. And at various times in that breakdown, it will turn green, and then it'll turn yellow. And, of course, the purple and the red, where there's hemorrhaging under the skin, that's where there's just blood right under the skin. So, again, biliverdin, bilirubin, those are the yellow and the green of bile. Biliverdin is. Bilirubin, the yellow. Also, the colors associated with bruises and jaundice, all right? When you get jaundice, that's basically because of the bilirubin in your blood. Bilirubin transported in the blood to the liver and converted to bile, which passes into the intestines. That's why it's called bili. That's for bile. So ultimately, your red blood cells, after they get old, they have to be recycled, they get broken down. The heme pigment ultimately produces bilirubin, taken to the liver where it's used to make bile. And that's why bile has a yellowish and greenish color from the bilirubin and the biliverdin. Bilirubin is converted to urobilinogen by microbial enzymes in the large intestine. So urobilinogen is a precursor molecule. Urobilinogen in turn is converted to stercobilin, which is a brown color excreted in the feces, and to urobilin, yellow, which is excreted in the urine. So ultimately, the reason that poop is brown and your pee is yellow is because of hemoglobin. What started as a red pigment, after it was recycled and broken down, turned into a brown pigment and a yellow pigment. That's how you get all those different colors. So there you go, recycling of heme, biliverdin, bilirubin. Jaundice is when bilirubin accumulates in the blood. You can see there are the bruises. You probably had bruises like this. Go through all those colors. Yeah, that's because the heme group is breaking down and making biliverdin and bilirubin, and plus, of course, you've got just the blood pooling under the skin that will make the red and the purple colors and so on. All right, so that's jaundice. That's where it comes from. Too much bilirubin in the blood. And here's a former student of mine, Jill. She was at a football game, and a fight broke out at the game. And somebody bumped into her, and she went over the seats, the row of seats, and banged up her leg. And so she took a video and sent it to me so that I could see her bruise. Damn, look at that. Poor little Jilly. You can see there's yellow in there. There's kind of greenish. Jilly, by the way, one of my best students ever. And she went to nursing school there. She stopped by on her first day of nursing school wearing her brand new green scrubs. She stopped by my classroom. We took a little picture together. She started crying. And then she went home and printed it out and put it on her corkboard, and she sent me this text with it circled as a heart. And I said, Julie, that's really creepy. I want you to take that down right now, okay? Julie's a cool kid. Here's what Julie looks like when she's had a couple too many beers. She also paints my fingernails for me. I'm so happy. That's part of the bad thing about the pandemic. Julie hasn't painted my nails now in quite some time. Here you go. Recycling red blood cells, the epic movie. All right, there you go. Look at it over there on the left, 1 and 2. You see it getting broken down. Globin turns into amino acids. Those are totally useful. Heme, the biliverdin, the bilirubin. Iron transported by the transferrin to the liver. The bilirubin, the urobilin, the urobilinogen, the stercobilin, and so on. Okay, so there you go. The epic movie, recycling of red blood cells. Okay, predict the outcome of an overdose of erythropoietin. A, blood viscosity increases to levels that may induce heart attacks or strokes. B, the oxygen carrying capacity remains unchanged despite elevated red blood cell counts. C, red blood cell counts remain the same but the amount of hemoglobin increases. D, red blood cell counts increase but the oxygen carrying capacity decreases. E, red blood cell counts decrease, but the amount of hemoglobin increases. So 4 of those are just gibberish, and 1 of those is actually true. Which one is true? There it is right there. That's one of the dangers of the people. They call them blood dopers. Take things like erythropoietin. It causes you to make more red blood cells. You can carry more oxygen, but also remember what's the main contributor to viscosity in your blood? Red blood cells. So your blood can get so thick. Remember how the red blood cells we saw in that picture can just barely squeeze through capillaries? Well, too many red blood cells, they may get stuck. You end up with a little blood vessel bursting, and if that bursts in your brain or in your lungs, you end up with a stroke or with pulmonary edema. That's bad stuff. Dangerous. Don't cheat, kids. Play by the rules. The purple and the red is just the blood pooled in there. Awesome stuff, huh? I said, Jilly, way to go, girl. Nice work. Way to get it